Hello and welcome back to Calculus 2. Tonight we are going to talk about the life-changing section, right? We are going to talk about the improper integrals. These are connected to definite integrals, and from this lecture on, in all of the calculus courses, differential equations, all of your engineering courses in physics and everything else, you will always have to watch for this. Because you can end up with wrong answers easily, and situation usually manifests itself as explosion when you are designing things. That's how they miss, the battery stuff and so on. So the goal is to learn improper integrals, which is type 1 and type 2, where the type 2 is the one that it's the scary and important one, and type 1 is easy to spot and easy to deal with. So let's talk about the idea first of all of this. So let's go back to what we have, where the definite integral computes area under the curve. So if the function is not crossing the x-axis, right? If the function is strictly above x-axis, between A and B, we're going to have an area, and that will be the area A that we can calculate with our integral. Can be related to energy, can be related to voltage, can be related to accumulation of money, can be related just to plain area of objects and things. And we see that our shape, which we are considering here, the f of x, right, is bounded. In this case, looks like 4 sides, even though one on top is wavy, is a curve, right? And the question is, what if area is in some sense leaking? Let me give you an example. If you take function e to the negative x, right? So that's a decay function. And you draw the graph, right? That will go forever. Has some y-intercept, whatever, right? And usually x-axis is time, right? If you're measuring decay of mass, decay of garbage, decay of radioactive materials and stuff. And you want to calculate area, but you are going to let the time go forever. We see that area is leaking over here and going forever, but the question is the area finite or is the area infinite, right? So in this case, you would be looking for area, let's go 0 to infinity of e to the negative x dx. And the question is, this function e to the negative x will never cross x-axis, which means it will never create the bounded box, right, for the area. But is the area infinite, right? Which kind of makes sense to claim. But we'll see that in this case, it's not. So that is the easy case, where you have an infinity or negative infinity in your limits, and you deal with that. The scary part is the second one. the one that has a vertical asymptote. Because if you miss that asymptote, if you are not good with functions and analyzing functions and not catching the asymptotes, if you integrate over the region which contains an asymptote, most likely you should get unbounded, meaning infinite integral. But your calculations might say it's finite. And you go forward with the design and your prototype goes kaboom, right? So if I have, let's say, g of x to be 1 over x minus 3, let's say, that would be a rational function, right? 1 over x, which is shifted 3 units to the right because it was minus 3. So you would have this situation. And now, right, if you are to calculate the area from, let's say, 0 to, or let's go 1 to 5, whatever, it doesn't have to be symmetric. Let's go 0 to 5, whatever, right, of 1 over x minus 3 dx, right? The question is, what's going on? Because look at your area, right? If you're starting at 0, you have all of this, which is going to leak this way. There is a 5 over here, which is that, and it's leaking in these two ways. Now, would that be finite? Would that be infinite? Right? So remember that you can represent energy, right? You can represent energy with a integral that it's definite integral from value to value. You can represent the amount of energy, accumulation of all energy in the system. Well, if that number is infinity, that means that the energy is trying to go to infinity. Over a short period of time, that's what the explosion is, right? Release of huge energy in short period of time, right? So what we are going to do today is we're going to understand the type 1. Oops. So Roman numerals, right? Type 1 and type 2. Where clearly the one on the type 2 is the one that is dangerous and one that it's difficult because, again, you have to be vigilant, right? You have to know that there is an asymptote, that there is a discontinuity, that there is a problem, so you can adjust your calculations accordingly when you are solving. So it's not just, stick this into a computer and get the best number you can, right? It is also, you have to analyze these things and try and figure them out. There is nothing out of the ordinary, right, in this integral if you don't know that something bad is happening, right? If you look at it, you say, oh yeah, this is just a basic u sub, it's ln of x minus 3, you just, you know how to solve this. But the issue is, right, the issue is that it goes over the asymptote and the area under it might be infinite, and that's a problem. So that's why these type 2 are scary, right? You have to recognize them. And that's why I listed all of the courses that you will ever take after tonight's lecture. All of them, right? Because they show up in Calc 3, they show up in differential equations, they show up in thermodynamics, they show up everywhere, right? And if you're not able to recognize them, then there's an issue. All right, so let's do all of this in order. So we go type 1. And type 1 is easy, right? So for type 1, you're going to have a to infinity, or negative infinity to b, or negative infinity to positive infinity. The obvious thing is here is you can see it. You see infinity in the limit, and you know that you have to be careful, right? Because you are dealing with infinities, and you know that you are not supposed to have infinite energy or infinite money accumulated, right? Because those things just don't happen, right? Everything is finite. So the question is, how do we deal with these things? Well, if you have the integral from a to infinity of, let's say, f of x dx, you can make it, leave some space, you can make it into a finite a to b f of x dx, and then send b to infinity in the limit. So it's a nice little hack way to do this, right? To figure these things out. And you will do the same for, pretty much everything else, right? You will have your negative infinity to b of f of x dx to be limit. Now you're sending a to negative infinity, the lower limit, right? A to b f of x dx. So this is your regular Calc 1 integral, right? You just solve that, and then you use the limit in front. Now, clearly, the answer would be in terms of a, and then when you plug in, infinity, you figure out what to do. And in the third case, these problems are rare. I mean, they're around. I'll give you one that it's used all the time. Negative infinity to positive infinity of f of x dx. You need to use the theorem from Calc 1, which tells you that the definite integral can be broken at any point inside the domain. So you can just pick a value, any value. We can pick c, and go negative infinity to c f of x dx plus c to positive infinity f of x dx, which would give us limit a goes to negative infinity, integral a to c f of x dx, plus limit b goes to infinity of c to b of f of x dx. So these are the three, right? These are the three possibilities where the top is, right? So these are like, it's all just replacing an infinity with a limit. I hate to call it three cases because they all use the same trick, right? You are creating a definite integral out of the infinite integral, right? You're creating a definite integral, and then all you do is you replace that value, you send that value to appropriate infinity. That's all it is. So technically, I mean, I can put a, b, c on it, but when you are remembering these, plus this one is a combination, right? This is your b part and this is your a part. I mean, that's what it is. It's just how to deal with both infinities. You have to have this intermediate step. Cool. So now let's take a look at that e to the x situation we had. So let's say 0 to infinity of e to the negative x dx, right? We have seen the graph, right? We know what it means. It's a decay. Decay means it will never go away, the value. And since we're going to infinity, we start at 0 and we are going to infinity. And we have all of this area underneath, right? And that area is leaking to the right forever, right? So it never stops. Now the question is, what is happening with the value of the integral? So we have limit, and we are sending, right, the top limit is b, right? So we're sending b to infinity in this limit, right? You had a positive infinity in the upper limit. and you just have your e to the negative x dx. So you use your limit, b goes to infinity, and you have e to the negative x over negative 1, right, when you integrate e to the negative x, and you have your 0 to b. So now this is limit b goes to infinity of negative e to the negative x from 0 to b. And now just use calculus 1, right? I mean, all of this is calculus 1. You just stick the limit in front. That's still calc 1 concept. I guess when you put two calc 1 concepts together, you get a calc 2. 1 plus 1 is 2. There you go. So we have limit b goes to infinity, and you have negative e to the negative b minus negative e to the 0. So now you are going to, use the limit. So how much is e to negative infinity, right? And that part is 0. So this thing goes to 0. You can see it on the graph up there, right? When you have e to the negative x, right? As x goes to infinity, your y value drops down to 0. So if b goes to infinity, the e is then you have e and then negative, right? So it goes to 0. You don't put negative 0, it's just 0. So you have 0 plus 1 equals 1. So we have a finite area. I'll write it down. We have finite area of 1. That's what we have. Finite area of 1. Even though the area is not boxed in, right? It's leaking area in one spot going on forever. So that's one of the examples. So let's take a look at a couple of more of these. Type 1. I'll pick something out from homework. So as long as you are able to integrate, which is right at the beginning of this chapter, you will replace, with the limit, the infinity, and you just go from there. So let's find something that is not e. Oh, this is a perfect example that I guess everyone is going to hate, right? Because it's partial fraction decomposition. Actually, no, let's go easier first. So let's go negative infinity to 0 dx over cube root of 2 minus x, right? So this would be considered as a cheap, right, integral, because this is a basic u sub, right? Now we see infinity, so we start immediately with the limit a goes to negative infinity, y a, because the bottom limit is a and the top limit is b. So if you're replacing the bottom value, you replace it with a. So we have a to 0 dx over cube root of 2 minus x. At this point we use u sub, so u is 2 minus x, du is negative dx. When you take the derivative of 2, you get a 0. When you take derivative of negative x, you get negative 1. We don't have that negative, so I will put in the negative. You can put negative in front of ln. Don't put the negative in here, because then it makes no sense. I mean, you can put the negative there, but then you have to put parentheses like this. So it's just more work. So we have now negative limit a goes to negative infinity and we go and say we have we'll go back to x values, right? So let's keep the same. I mean, we could change the limits, but then it's going to be more problems. Du over cube root of u, right? Which is actually a goes to negative infinity, a to 0. This is u to negative 1/3 du. Negative limit a goes to negative infinity. Now we are integrating, so u, we do +1, right? So that's u to the 2/3 divided by 2/3, a to 0, and then limit a goes to negative infinity. That's 2/3, no, 3/2, sorry, 3/2. So 3/2, u is 2 minus x, right? 2 minus x raised to the 2/3 from a to 0. Now the 3/2, right, is a constant. We can kick that outside. So now we have negative 3/2. We have a limit. A goes to negative infinity, and then I have 2 minus x to the 2/3 computed from a to 0. We plug in these values and we see what we get, right? So negative 3/2, limit a goes to negative infinity, top limit, that's a 0. So they're just 2 to the 2/3 minus, and now we have 2 minus a to the 2/3. Now, I hope you see that when you plug in negative infinity in quotation mark, right, plug in, you are going to get infinity for this term, right? So positive number minus infinity is going to give me negative infinity, and then times the negative number in front, this is equal to positive infinity, and we will say the problem diverge. Usually we just put a D in this one for divergence. Now, diverge literally means divergent, right? You have a road and diverges into two roads, right? Divergent. One goes away from the other. So, divergent means goes to infinity, right? Goes to positive or negative infinity. That's what it means. Now, for you guys, it's sufficient to write diverges. It's sufficient to write D in a circle like this. If it was a paper test, it's just sufficient to say it's divergent. Right? That's all we have. And here is the case. That would explode. If you are to design something like this, then the buildup of energy is infinite, right? Because this is the answer. It's equal to infinity, right? Previous answer was equal to 1. That one converges to 1, meaning that the area under the curve, which could be accumulation of money, so great. For whatever, you wait infinite amount of time, and what you make is $1. Right? So in infinite amount of time, you made $1 or $1 million or 1 billion or 1 trillion, I don't care, right? The trick is you get one of something, right? So if you were going to have 1 billion population, 1 billion of puppies if you infinitely breed, right, forever. So whatever the weird example I come up with, right? So convergence and divergence in this case, right? We are looking for the final answer to be either a finite number, which is convergence, or positive or negative infinity, which is divergence. And that's That's what we have. Now let's take a look at one more of these and then go to the type 2. Now I was thinking of that partial fraction decomposition. I'm kind of lazy to do it. Well, let's do it, whatever. 32. See, this has nothing to do with the methods of integration. You can get any method of integration inside these integrals, because this is something that you are talking about regarding all definite integrals that exist in every aspect of our human STEM existence, okay? So, you know, mathematical biology and fluid dynamics and electrical engineering, right? So this is a concept that deals with infinity. Methods of integration, well, whatever you have to do. So in this particular example, as you can see, you have partial fraction decomposition, right? This is a partial fraction decomposition problem, which is packaged with improper integral type 1, where we have to go with the limit b goes to infinity, and then we have 1 to b, and we have our dx over x squared x minus 1. So we have to do our setup. So a over x plus b over x squared plus c over x minus 1 needs to be equal to 1 over x squared x minus 1, right? That's all we have. Now it's time to multiply what's missing for the common denominator. So this is the easiest one, right? X squared is missing. Over here is x minus 1 that it's missing. And on the first one is x squared minus x, right? Because you are missing the second x, and you are missing x minus 1. When you distribute x times x minus 1, you get x squared minus x. Now we know we can drop the denominators. By now you should be, you know, PhD in partial fraction decomposition. So we have ax squared minus ax plus bx minus b plus cx squared equals to 1. So you have your a plus c. Okay, let me write that's x squares. These are x's and these are constants, right? So a plus c for x squares, that's equal to 0. There is no x squared on the right-hand side. Then we have negative a plus b equals 0. Those are the x's. And our negative b equals 1. Oh yes, that's the one that saves our life over here, so we don't have to suffer through 3x3 system. B is immediately equal to negative 1. If b is equal to negative 1, then a is also negative 1. No, yes. A is negative 1. So negative and negative will make a positive, and then minus b, yeah, minus 1. Good. And c is positive 1. Good. So now I have my limit. B goes to infinity. One to b. Then we have negative 1 over x minus 1 over x squared plus 1 over x minus 1 dx. We integrate this like nothing is happening, and then if any of these, just one out of 3 goes to infinity, it's gonna, you know, mess it up for everyone else, right? We all know the rule. You only need one SJW to spoil the fun for everyone else, right? So just one of these, and, you know, everyone else. So let's go. Limit b goes to infinity. We have negative ln of absolute x. Now this is going to be 1 over x, so plus 1 over x, plus another ln of x minus 1, and this is computed from 1 to b. So we have a limit, b goes infinity, and you have negative ln b plus 1 over b plus ln of b minus 1. Then minus and minus will give me plus ln of 1 minus 1, because there is a minus in the formula, right? And finally minus ln of 0. Now, when you plug in infinity, we know this one is going to go to 0. Ln of 1 is 0, so those terms don't bother us. We can combine these two terms into ln of b minus 1 over b, which is ln of 1 minus 1 over b. And when you send b to infinity, that term, right, because this term will go to 0 because 1 over infinity, the whole term will go to 0. And then you have minus 1, which is also cool. So we have all of these zeros, right? We have minus 1, and here is the one that spoils it for everybody. ln of 0. ln of 0 is negative infinity, and the minus in front gives you positive infinity, and the whole thing explodes. Divergent. One more time, your graph for ln. I mean, you better know this, but whatever, let's write it. You see that as you are going on x-axis, as you're going closer to 0, because this is ln 0, you see that at 0 you have negative infinity. And that's a problem. Right? That's a problem. That's the one that creates infinity in this case. And you know what? This particular term is the term that comes from type 2. So this is our segue into type 2. Sponsored by type 2. So let's talk about type 2 so we can understand it. So this is a scary one. This is a scary one because we don't necessarily see it, we don't necessarily recognize it, and if it sneaks in, it always makes a lot of mess. So I want to work on the easiest problem. So type 2, type 2, let's go, let's say, I just want to see how should I phrase this. Type 2 occurs when we have vertical asymptotes, or type 2 improper integration. I don't know how to. So let's go this way. Blood. Hold on. There we go. If f of x has a vertical asymptote anywhere on AB, including the endpoint. So this is closed interval. If f of x has a vertical asymptote anywhere on AB, then we must use type 2 procedure. All right. Our example from earlier was, I believe, 0 to 5, 1 over x minus 3 dx. Now, instead of having the asymptote on both sides, I'm going to make this a little bit shorter for us, and we'll go back to the, more calculations. I'm going to make this a little bit shorter and just going to say 3 to 5, okay? I'm just going to do 3 to 5 because it is a little bit easier to compute. All right, cool. Now, so I changed the problem a little bit so we have less writing and less steps. So that's our problem. And I want to integrate this. Now, we know that vertical asymptote is at x equals 3. And that is a problem, right? So we are going to start with the limit. X approaches 3, and it's approaching 3 from the right. So 3 plus. It's a one-sided limit. And we have integral, sorry, not x, a, lower limit, a to 5 of 1 over x minus 3 dx. Now, this is our basic ln integral. We know those from our section on partial fraction decomposition. We've seen them so many times. So we have our limit. A goes to 3 plus. And the integral over here is just ln of x minus 3, right? From a to 5. Three plus ln of 2 minus ln of a minus 3. So ln of 2, that's a number. We have nothing to do there, right? The question is, what is happening with ln of 0 as you are approaching from the right, right? Because when you plug 3 in here, you're going to have ln of 0, and you will be approaching it from the right. Well, if you draw ln of 0, and you approach it from the right, you get your negative infinity. So, this turns out to be ln of 2 minus negative infinity, so the whole thing is infinity and diverges. So let's put a goes to 3, which, right, this is ln, that gives us the 0 there, and right. So, wow, right? We have something that was so easy to integrate, and all of a sudden, right, infinity. So now I hope you see that we have to be very careful. Similarly, for our friend, let's go 0 to 1, for 1 over x dx, this is a quick one, right? It's the same as the above. We know that the problem is at 0, so limit a goes to 0 plus. Plus means approaches from the right. Integral 1 over x dx from a to 1. So whatever is problematic, you replace that with the limit. So now what we do is we integrate, we get our ln absolute x, right? So 0 plus, we get ln absolute x from a to 1. And this is the limit a goes to 0 plus. You plug in ln of 1 minus ln of a. Ln of 1 is 0, so we don't have to worry about that. And you have negative infinity, which is positive infinity, which is divergent. I mean, we were not expecting anything else. The upper integral is just moved 3 units to the right, so we can't expect to get non-infinite answer, right? Now, I did this problem for a very particular reason, because I want to now ask you to try 0 to 1 of 1 over x squared dx, right? So 1 over x had the graph that did this. The 1 over x squared has Atari graph, right? You're not old enough to know what I'm talking about. So there you go. You still see that you have a problem at 0, right? So if you are to plow through this calculation, knowing that you still have asymptote at 0, knowing that, right, you will be surprised at the end to see, right? Hopefully, if you wanted to do this, right, you paused the video, you did the problem, right, and now you're listening what I have to say. You are surprised to see that this one converged. So that square made the integral, drop to x-axis faster. I mean, function drop to x-axis faster than 1 over x, and because of that, it converged, which is very interesting. So any exponent bigger than 1, right? So 2, 3, 4, and so on, they all converge. But let's just do calculation. Oops. So we have our limit of a going 0 plus, right? And we have our a to 1. We are integrating x to the negative 2 dx, right? So no more ln. And now I go and say, what do I have here? This is going to be limit a goes to 0 plus. What's going on? X minus 1 over minus 1 from a to 1. Wait, hold on. Limit a goes to 0 plus. Now this is negative 1 over x minus, and minus will make a plus 1 over a. I mean, this was supposed to be a 1, because when I plug in values, you plug in upper. Oh, no, I said it wrong. Sorry. This one converges on a type 1, not on a type 2. Scratch it. This one's going to diverge. Well, there's correct calculation at least. Limit, when I integrate this, when I compute, it's going to be negative 1 plus infinity divergence still. If you do this from 1 to infinity, 1 over x squared, so type 1, that one is going to converge. Sorry, I messed it up. So this one still diverges, right? And the type 1, since I hyped it up, I just now have to write. So type 1, integral 1 to or 0, whatever, 0 to, no, not 0, 1 to infinity of 1 over x squared dx converges. I mixed them up in my head. So type 1 converges, type 2 diverges. Ah! Bad day. Bad day. Let's pick something in the book. By the way, we are done. That's it. You know both of them. Type 1, you see infinity, you replace it, you plow through calculations. Type 2, well, if you have a vertical asymptote somewhere, right, then you have to examine that and deal with it. So let's find the problem that can make issues. Here's a nice one, 43. It says integral 0 to 1 e to the root x over root x dx. That's it. So problem 43 in the textbook. So 0 to 1 e to the root x over root x dx. Well, I don't need much to realize that 0 is a problem, right? Because the root of 0 is 0, and that's just going to make 1 over 0 undefined. So clearly 0 is a problem. So limit a goes to 0 plus, we are approaching from the right again. And we have a to 1 e to the root x over root x dx. Now, u sub should be obvious to you by now, right? Because this is, u is root x, and du is 1 over 2 root x dx. I don't have a 2, so I'm going to put that 2 in the problem. So 2, limit a goes to 0 plus. And I have to go back to x's. I mean, I don't have to, but then I just have to drag root a through the calculations. So I'll go back to x's. So I'll keep a and 1, right, quickly over here for e to the u over, sorry, e to the u du. So, 2, limit a goes to 0 plus. And then e to the u, so that means e to the root x from a to 1. Promising, huh? Limit a goes to 0 plus e to the 1 minus, well, just e, right? Because square root of 1 is 1. So e to the 1 is e. Minus e to the root a. But a is going to 0. So this is just 2e minus 1. Converges. You can punch this into your calculator, get the decimals if you want to. It's about 3.4, right? For this value, 3.4. So it's not that bad. It's easy to compute. So there is another type 2 integral. Did not look bad, right? Using basic u sub. So this is technically calculus 1 integral if I put limits 1 to 3. Or 1 to ln 7, right? So if I use any limits away from the asymptote, it's a basic Calc 1 problem. But if I put a limit of 0, well, then it starts climbing the vertical asymptote, and that could introduce infinity, and we have to deal with this. Now, for some problems, guys, you are going to have to use L'Hopital's rule to find the limit. Remember when you divide when you find the derivatives, right? Independent derivatives for numerator and denominator, and you go from there. So some problems will require that because the limit is going to be harder than the integral. So these problems kind of combine, a couple of sections of calculus together into one, and it's good luck what you get on the other end. You can have trig sub inside, you can have the regular u sub, you can have the line integrals which we had, basic polynomials might be floating about, a lot of, and then you, in addition to, having a headache of improper integrals, you also have to think what is the appropriate integration method, and all of those things. The only thing we can do is another problem, I guess, because why not? So what do I see over here? What is this witchcraft? 58 looks absolutely disgusting, which is awesome for us because that's what we like. So from negative infinity to positive infinity, and then we have x squared plus 2x plus 5. What now? Well, remember what we said earlier? You get to break your integral at any point you like, because you can't put two different limits in the same, right? So we have to split this into two integrals, and when we split into two integrals, we have to pick a point where to split, and clearly between negative infinity and positive infinity, the easy point to compute that would be 0, right? So I'm going to make this negative infinity to 0 plus integral 0 to infinity. As you can see, I did not write everything out, which is terrible. But now in this step, we are going to write everything out. So limit a goes to negative infinity, integral a to 0 of dx over x squared plus 2x plus 5, plus limit b goes to infinity of 0 to b dx over x squared plus 2x plus 5. So now we need to integrate, right? We know what we're going to do with these limits. The question is what we're going to do with the integral. And the integral, clearly, no one wrote it yet, which makes me sad. The integral clearly needs to... Yes, completing the square and then completing the square and then trig sub. Right? It's a technique. So let's go. We have x squared plus 2x plus 5. Now, those of you that are quicker with these things can also recognize this. And then you immediately see x plus 2 squared plus 1. Right? So if you see the square of the binomial there, it goes and, right? So we're just going to integrate, and then we're going to plug everything in. So now I have an integral of dx over x plus 2 squared plus 1. So now I have my triangle for trig sub. I mean, if you already see that this is inverse tangent and you are able to do that quickly, then you don't have to mess with these things. This is inverse tangent problem. Inverse tangent of x squared plus 2. It's, if you did enough integration, you just know. But we can also do it. There is a plus which means these are legs, which means this is a square root of x plus 2 squared plus 1. We have our red function over here, which is tangent theta x plus 2 over 1, from where x is equal to tangent theta minus 2, and immediately dx is equal to secant squared theta d theta. So we have to have that. And then we have the blue equation, which is this mess. That will be our lovely cosine theta, which is equal to 1 over the square root, from where the square root is equal to secant theta. Now we need to square both sides to get because this one does not have a square root, right? So when you square both sides, let's do that in different color. There we go. You will get x plus 2 squared plus 1 equal secant squared theta. Good. So now when we plug everything in, we have integral dx is equal to secant squared theta d theta divided by secant squared theta, right? Because that's what it is. And then they cancel completely, and you just have integral of d theta, which is theta. We don't need plus c because remember we have definite integrals later on to deal with. So we just need what theta is equal to, and theta is equal to inverse tangent of x plus 2, which is equal to inverse tangent of x plus 2, as I promised, right? You can put plus c so our allergies are not kicking in, right? Now go back to our problem. So you work this out in the margin of the book, and we go back now to our problem up there where we have the limit. I forgot what it is. Here it is. So this part, right, where every integral will be replaced with inverse tangent. So a goes to negative infinity of inverse tangent of x plus 2 from a to 0, plus limit b goes to infinity of inverse tangent x plus 2 from 0 to b. If only one of these goes to infinity, right, I'll have 4 terms when I expand everything. If just one of them goes to infinity, the whole thing diverges. All right, let's go and see what we have. We have tangent inverse of 2 minus tangent inverse. This is a terrible thing to write, but what I'm going to do, of negative infinity. This is mathematical sacrilege, but yeah, it's shorter. Plus tangent inverse of infinity minus tangent inverse of, when you plug in 0, 2. Now we immediately see that these two cancel because they are the same term with opposite signs. That's easy. And I have these two terms here. Now, if you recall the first day of our course, I said, yeah, you gotta know those inverse tangent graphs, right? Because if you don't know the inverse tangent graphs, some of your problems are not gonna work out very well. So this is the inverse tangent graph, right? Like that. So we have negative, right? This guy canceled. The first term canceled. So we have negative infinity. This is where negative infinity is, and it's giving us negative pi over 2 as the answer. That's negative pi over 2, and that's positive pi over 2, right? So that one is this. And then we have plus tangent of infinity goes this way. So pi over 2 for a total of pi. Right? So pi over 2 plus pi over 2 is pi. And there we go. That's what it is. So we have completed the problem. It's a long problem because we had to use trig sub. If you don't know the formula for inverse tangent for integration, which was on the list of basic integrals in 4.9, then it was on the list, and whenever we did it again, we had at least 3 times so far. Inverse tangent is listed as one of the basic integrals, right? But again, luckily we can use trig sub to get there, except it takes long, right? I could have skipped all this work, but there you go. There you have it. So that's it, guys. That's integration, improper integrals, right? Improper integrals, we have a type 1 and we have a type 2. Type 1 improper integral is going to be given by in infinity. So you have infinity somewhere in the limits. And the type 2 has the vertical asymptote that you have to spot. And once you spot it, you have to work around it. And every of those asymptotes or infinities have to be replaced by the limit. You have to use whatever integration you have, right? You have to use whatever integration you have to solve the problem. So that could be partial fraction decomposition. You saw that. It could be trig sub. You saw that. Basic U sub. You've seen that. We didn't do any of the by parts, but hey, that can be there as well. We can easily make the problem for by parts, right? If you want the by parts problem, you don't have to go far. You can just say, how about 0 to 1 x ln x dx? There's your by parts, right? I'll assign this one. I'm not going to do it. I'll just say by parts, and right, good luck. And finally, here I'll just put the symbol. It's ugly, but you all know what it means. You can type in a chat. You all know what it means. And I'm just going to write this at the end. Type 1 and type 2 can be mixed in the same problem. So they can be mixed into the same problem. So you can have something that has an asymptote, but it also has an infinity. Actually, the problem that I did earlier was one of those when I said sponsored by this one. Yeah, look at that. When you plug in 1 in here, you get the 0, so there is a vertical asymptote at 1. See that? So I didn't do this problem well, right? Go to the end for fix. Go to the end for fix. Now, why do I say that? Because I actually didn't do a good job. I mean, we're going to end up with the same answer because it is going to diverge. But I didn't do a good job in setting it up. So that problem, which was the... I lost it now. I don't want to scroll up again. There it is. So that problem 32 was 1 to infinity. Yeah. 1 to infinity dx over x squared x minus 1. Okay. So what I should have done, I was just shooting for the problem with the infinity. I didn't check and then I messed it up. I realized it at the end, right? I wrote it in blue. But still, the procedure to solve the problem was not correct. So let's upgrade it. Let's make it good. I'm going to break this integral 1 to 2 because we do have a problem at 1. Let me write it this way. Type 1 and type 2. So we have both types. And because I have to use two limits, then I better break it into two integrals. So I'm just going to make any point, right? I'm going to break this at any point from 1 to infinity. You can pick whatever you want. If you like pain, just use e to the pi. It's fine. So I go 1 to 2 plus 2 to infinity. And now I introduce the limits. So limit 1 is a problem. So a goes to 1 plus because you are approaching 1 from the right. The rest of the function is to the right of 1. So you are walking from the right towards 1. That's why we put plus there. Integral a to 2 of dx over x squared x minus 1 plus a limit b goes to infinity 2 to infinity dx over x squared x minus 1, right? So this is the proper way to do the problem. Now it's still going to be insert work here, which is what we did up there. Same integration, partial fraction decomposition, blah, blah, blah. And you get your divergence at the end because you'll have that ln term that is going to ruin everything. So this is a section on improper integration. Please watch some of the older videos as well for different examples. There should be at least 10 different integrals, 10 different lectures, and they all pretty much have different examples in them because I always do different examples. So look up old video lectures for more examples. Now we are done with chapter 8. And the next chapter for us... Oh, by the way, when I say look up old video lectures, section 7.9, because I think in the old book, I have to verify that if I don't have the copy of the... I don't have the copy of the old textbook. I only have this edition. And I'm drowning in Larson books. I have 3 of them here. Well, actually, hold on. I can probably go to one of the old Calc2s. Let's see. Yes. 7.8. There we go. So 7.8, you will be searching 7.8 on my channel, Improper Integrals. For more examples and more instruction on this one. All right, so Thursday, we are going to take care of the two sections that we are covering from chapter 9. We're only covering sections 9.1 and 9.3 regarding differential equations. So chapter 9 has 5 sections on differential equations. Now, we have a whole course on differential equations. You can just tune in every Monday, Wednesday at 11 and just learn difficulties there. So we are only going to cover those sections. The first one is what differential equations are and stuff like that. 9.3, separation of variables. We are done with the material for the second exam. We will be done with that on Thursday. So I hope that a lot of you will be on during the live lecture. I will also post the announcement. We need to start talking about exam 2 because we have 6 weeks left, I believe, and in those 6 weeks we have to have exam 3, final exam, right? And I'm trying not to, have a lot of that stuff at the end of the course when everyone is going to have everything, right? Because this is not the only course you guys most likely are taking. So the sooner we get exam 2 off of our backs, maybe even next Thursday. I don't know how well and how far you are with learning these, but hey, the 2 weeks of spring break and all the quizzes and everything else, I hope you are pros in chapter 7 by now. I mean 8, sorry, 8. So we'll have another discussion on Thursday. So both sections that we are covering from chapter 9, so 9.1 and 9.3 will be covered on Thursday, and we will be done with the material for exam 2. So look for my announcements, and that's it. I will talk to you soon. Bye.